So for definitions of terms and terminologies, okay, for the cycle, cycle is defined as the movement of the vibrating body, so from its undistributed or equilibrium position to its extreme position in one direction, and then to the equilibrium position to extreme position in one direction, back to its original position called cycle or the vibrations that will be equal to one revolution. Now, for example, here, slighted pin, you will notice here. So initially started from 0, so so the vibrating body, so from its undistributed or equilibrium to extreme position. So initially we have extreme position started from here, then it's go back to its original position. Then so this is one goes to one direction and then go back to original position. Then it reaches to an extreme position, but it is on the other direction. So you will notice here, so up and down. So that corresponds to one cycle. So this from here and this one from here. So this defined as a one cycle or cycle. And also that is the same here. So for this rotating vector OP, so starting from its original position, then to its maximum position, go back to its original position, but on opposite direction. Okay. So that describes one cycle. Now for the maximum, for the amplitude, okay, so we have the amplitude. Okay, so that is defined as the maximum displacement of the vibrating body to its equilibrium position, and it's called amplitude of vibration. Now you will notice here, we have here the amplitude. So here, that is the amplitude for this one displacement, which is your maximum, that will be corresponding to the amplitude. Then this one also for this type of vibrating body, rotating body. So we have here the amplitude also, that is from the maximum, and this is for one direction. And also this one, we have also the amplitude which is in the opposite direction. So that defined as your amplitude. Now for the period of oscillation, so it is described as the time taken to complete one cycle of motion, known as the period of oscillation, or the time period, and it is denoted by the symbol like this one. So it's like a shear, no? But it's a tau symbol. Now this defined as, for example, the time required for the vector OP to take rotate into a one cycle of 2 pi. So that is one cycle. So the time period it reaches into a one cycle, so that is a period of oscillation, and it is defined with the equation. So that is equal to your 2 pi divided by the angular velocity. Now for the frequency of oscillation, so this is defined as the number of cycles per unit time, and it is also called the frequency of oscillation, or simply equal as the frequency. So it is denoted by the symbol F, like this one, small letter F, and it is equal to your period of oscillation. Okay, and this is equal now. So since your period of oscillation is equal to 2 pi, so we can express this one as a angular velocity over your 2 pi. Now for the phase angle, so it is denoted with the symbol phi, no? So this symbol, okay. So for example, two vibratory motion. So for example, means ng phase angle. So that would be example, no? So this is x of 1. So I have my amplitude 1. So that would be sine, of your angular velocity times time. Then you have your another motion, so that will be phase of 2, then sine of we have your angular velocity times time, then plus uh, the angle, phase. That will be the phase angle. Now, the two harmonic motions given by these two equations are called synchronous because they have the same frequency or angular velocity. Now, from the figure, so let's have a figure. Now, so this can be said as a synchronous because again, so they have the same frequency, and you notice here the angular velocity of symbol. They have the same or equal angular velocity. So you will notice here. Let's try to zoom in. Okay. So that is that my OP1 as a given angle of theta 1, so that is equal to the angular velocity times time. Then my OP2, that makes an angle, starting from piece of OP1, so that will be have a corresponding angle which is your phase angle. So that is the phase angle. Then this is theta 2, so that is defined as the angular velocity times time plus your phase angle. So starting from here, that will be theta 2. So these motions are rotating in the same frequency, and the phase angle defined as the difference. You will notice here that is the difference of their the difference of angle between two vibratory motion. Or a synchronous motion with an equal angular frequency or angular velocity. So beat, so when two harmonic motions with a frequency that is closer, one another are added, so this resulting motion exhibit phenomenon known as beat. So consider two vibratory motion x of 1 and x of 2 as a function of time. So we have here the same amplitude for both of motion. Now, so where the small quantity of additions of your lambda or your call this values of your lambda here. Okay, so I can say that my x, so my x, okay, so that will be the function of time, so that is equal to your x of 1 function of time, so that will be the sum plus your x of 2 function of time, and this is equal to the sum of my function, so where my function x of 1, and that will be x, so that is cosine of your angular velocity times time, then plus the value of your x of 2, so that will be your x, that will be cosine angular velocity plus my lambda here, which is multiplied by time. And we can factor out the common here. Since I have my common here, we have your x. So what is left is my cosine times the angular velocity, cosine angular velocity times time. So this will become also my cosine angular velocity. You have your lambda, and that will be multiplied by time. Now I have my trigonometric identities, so that will be cosine of my angle A plus my cosine of my angle B. So this is equal to 2 cosine of A plus B divided by 2, close parenthesis, multiplied by cosine of A minus B over 2. Okay. So I can use these trigonometric identities to simplify further my equation for my B. So where is my A is equal to angular velocity times time, and my B is equal to the angular velocity plus your lambda here, then multiplied by time. Then I can write the equations here, substituting that one using these identities. I can say that my x, that will be x, okay, so that will be times 2 cosine, we have your angular velocity times time, that will be times your angular velocity plus your lambda, then that will be by time. So this is all over and divided by 2, okay, and multiplied by cosine. So this is close parenthesis. So the value of A, that will be angular velocity times time. Then the value of V, so this will be angular velocity plus my lambda here, and that will be multiplied by time, all over no? So this is all over by 2. So, and also close parenthesis. Okay. Then I can distribute this one, so that will be x. Okay, that is 2 cosine. So distributing this one, so I have this one, that will be 2 angular velocity times time, no? Then this is will be lambda plus lambda the time, and all over, this is all over by 2. Okay, so the close parenthesis, then you have your cosine, and we have here, if you're going to distribute this one, and this will be cancelled out, and what is left is my lambda here, then times time, and this is all over by 2. Okay, then close parenthesis. Then we can further simplify this one, so this will become my 2 cosine, and this will be cancelled out. So what is left is we have angular velocity times time, then plus my lambda here times time, and this is all over by 2. Okay, and this one, what's left is again keeping hold this same equation here, no? Okay, so I made the corrections on this one. So again, so I can rewrite this equation as my x, no? So this will become 2x. So close parenthesis on this one. So this will be cosine times angular velocity times time, then plus my lambda here times time divided by 2, and this is cosine, because we have your lambda times time here divided by 2. Okay. So, and we have the identities like cosine of my negative theta, so this is equal to cosine of theta. Okay. So I can change this one, so my beat equations now, where your x function of time is equal to 2x close parenthesis, so this will be cosine. I can factor the common here, so I can the angular velocity times time, I can factor the t here, so we have your lambda, and this is 2, then this will be multiplied by time, and this is will be multiplied to cosine, and since this one is negative, you can change the sign convention here, so this will be positive, then number 2. Okay, so this is now the equation for my beat, so the displacement of the beat. This is can be further be explained by this graphical representation, no? So we have here whenever the amplitude reaches to its maximum value, so that is what we call the beat, maximum value, that is what we call the beat, no? And the frequency at which the amplitude buildups and dies between 0 to 2x and 0 to negative 2x is known as the beat frequency. So we have here the beat period, and this is defined by this 2 phi, that is your lambda divided by 2 lambda. Okay, so 2x, okay, so that would be this the amplitude of this one.